So last week with Carly, we explored how ground truth technologies help us understand nature up close. Today, we're taking a big step back, literally, to look at nature from above. What we call remote sensing technologies are revolutionizing our ability to monitor ecosystems at fairly unprecedented scales. So from tracking deforestation across entire continents to detecting subtle changes in biodiversity over time. For businesses trying to understand how their operations affect and depend on the natural world, this overview is becoming increasingly crucial. Whether it's assessing potential project sites, monitoring supply chain impacts, or validating nature-based investments, for example, the ability to monitor vast landscapes is actually no longer optional, it's essential for making informed decisions. So we're privileged to have with us Dr. Greta, lead ecologist, and Luc, co-founder of and CTO at Versant. Together, they'll help us demystify the world of remote sensing, from understanding basic concepts like GIS to exploring how different technologies like satellites and drones work together to provide actionable insights for businesses and conservation efforts. So whether you're a land manager looking to track ecosystem health or a sustainability professional trying to monitor environmental impacts, or simply curious about how remote technology is advancing restoration, today's conversation will provide valuable clarity on these powerful tools. So Greta and Luc, it's really great to have you here. I'd love for you to introduce yourself first before we dive into the questions. Maybe Luc, you could start us off with yourself and more about Versant.
Sure. So hello, everyone. My name is Luc Bettaib. I am originally from the United States, but I'm living here in Paris, France now, where with my colleague and co-founder Martin, who is not here today, we started Versant. And what we're doing here is we are developing technology that helps companies in France comply with environmental regulations that they need to comply with when they want to develop new projects. So, for example, a solar panel project where they're installing lots of solar panels on some area, infrastructure with perhaps like wind, or new construction for like apartments or something like this. Anything that can impact and artificialize land over a couple hectares needs to comply with this regulation. And part of it involves understanding your impact on biodiversity. So what they do normally is they go to a consultancy and they get an impact report done. They try to understand how to minimize their impact on biodiversity in the area. So, for example, if there's a protected species in that area, perhaps a butterfly that's very important for the region, they need to design the project and choose where the project is to minimize that impact. If, according to the study, there's a residual impact that can't be compensated for, they're required to, with a multiplicative factor, find land nearby that can be restored. So there's additionality to sustain that species in particular. This also is done for wetland impact as well, notably. And what we do is we create software that accepts the impact type into our software and basically scans the entire area nearby to find appropriate parcels that could be indeed useful for restoration for that specific species. And happy to talk more about how we're doing it when we get into the details.
Thank you so much for the invitation, Paige. So I'm Greta Carrete Vega. I'm based in Spain. My PhD, Paige mentioned I'm a doctor, was on natural conservation of nature, and it was mostly in Antarctica. So probably one of the least biodiverse parts of the world, but it's a great place because it becomes a natural laboratory. So what I did a lot was to work on species distribution models. So to understand what are the conditions that make a species be where it is, and understand if it could be anywhere else. And that is a methodology that is very useful for reintroductions, to understand invasive species, and to understand also extinction of a species due to climate change. So now at Versant, after finishing my PhD, I focused on working on platforms, on web platforms that use spatial data to bring the information decision makers need to make decisions, particularly related to decisions that help conservation and restoration of biodiversity. So GIS stands for Geographic Information System. So GIS is a way of understanding and organizing data that has the element of where. So data you can describe things, and you can describe the color, you can describe the size. What you're going to do with GIS is to say where that color and that size is in a coordinate system. So what then happens is that a lot of that data can either be collected, like last week Carly was explaining, by going on the ground and with a GPS and say particular, I think she was talking about monkeys or some kind of ape, is and what it is doing and what is its characteristics. So another way of collecting this data is remotely, and that's where remote sensing comes into place. I've actually had to check, and remote sensing and Earth observation can be used actually interchangeably. So the idea is that you are collecting data from far away, and it's obviously data that is describing the Earth. Sometimes it's large areas. So for example, you were mentioning Google Maps. Google Maps, we use remote sensing data when we are looking at the satellite data that shows you what a particular area you're interested in, a city that you don't know, and you have to go from the train station to your hotel. It's going to show you the streets, it's going to show you the buildings from above. That is a picture that has been taken by a satellite. And then when you are willing to understand how you go from the hotel to the train station or vice versa, what you are doing is a GIS processing. It's called a network analysis. And what the GIS is doing there is analyze from this point to another point, what is the quickest way to go using the paths that already exist. In this case, either the streets or maybe the tube system, if there's a tube, or the bus system. So in a nutshell, Google Maps has coordinates. So that's where the geographic information system appears. There's remote sensing, because we do use the layers of pictures that are taken from space or from sometimes planes. And we're doing processing by trying to understand how do I go from one place to another.
So the ton of different levels of remote sensing can be satellite data, of course, which is what Greta referred to. There are different kinds of satellite data. We have like picture data, image data that can kind of span across like the entire light spectrum, essentially, not the entire light spectrum, but different kind of segmented chunks so that we can get interesting information about things that we're observing on the ground, perhaps with how it's reflecting a certain wavelength. These are typically called multispectral and hyperspectral sensors that are from space. These kinds of sensors can also be applied to other forms of remote sensing. So aerial imagery or drones, essentially, this is the gist of it. The other sensing modalities that are quite popular right now that we can talk about are SAR, which is synthetic aperture radar, which is a way of understanding kind of the contours and kind of features on the ground, and LiDAR as well, which is a technique that sends out laser pulses on the ground, and it is able to measure also in fine detail essentially the contours of the ground as well.
It's a lot of data that is collected. Like I don't remember exactly the figure, but the amounts of petabytes we're talking is not even terabytes, it's petabytes that are collected constantly. That needs to be somehow translated into something that means something to someone that is not a robot processing that information. And that's where data products come into place. So, for example, from a picture, if it's an area you know more or less, you can determine, oh yeah, this is a park, these are trees, this is a field, this is shrub. But a lot of these images are processed a lot now by AI actually, and what they produce are products like land cover. So it's going to be a map that has 10, 15 classes, sometimes even more, that classifies and tells you straight away, these are trees, this is water, and this is sometimes agricultural fields. It depends on how much training the model has and also the purpose of that data product. So We work a lot with these data products that are produced by institutions like Copernicus, by the European Union. Then each country tend to have also their own products of particularly of land cover. And the idea is how then we process that information to have something that a user that is not very technical can get some insight out of it and then make a decision with that kind of insight. So is what Luc was mentioning before, and maybe he wants to go a bit more on detail of what we do at Versant with these data products.
For example, what we're doing when we're analyzing each parcel that is potentially appropriate for these kinds of compensation projects that the companies are required to do, is we look at them and we calculate some statistics on them. And for example, with these statistics that we're calculating, we're using some raw satellite data. So we're actually looking at certain bands and how they're reflecting light. And through this data that we're getting, we're able to calculate certain metrics that are associated with the parcel's kind of general health. This is maybe we can discuss this further, but I think it's something that is quite helpful for us. Furthermore, what we're doing with land use data, for example, there are customers that can't operate on agricultural land. And so this is something that we can use to filter out different land types that are not appropriate for the restoration work that the customers need to do. From our customers, what we do is we get an impact report. And in this impact report, it'll say, well, according to our analyses, we need to find several hectares of land to compensate for a certain kind of species or a certain kind of like wetland compensation. Through that, what we do essentially is model the species in the area. So we do something called species distribution modeling that Greta is an expert on. And from that, we take a bunch of occurrences of the species and parameterize that and cross it with other kinds of data, such as climate data, and then understand what are the suitable areas for that species to live in. From there, we go on and filter out according to other parameters that are given to us by our clients. Say, for example, we were talking about land use, if they can't have agricultural areas because the Chamber of Agriculture in the area says, no, we're not doing this kind of projects with you guys, then we can filter that out. From there, we get like a clump of areas that should be suitable for the species. At that point, we need to check for additionality. And so what we do is we run it through something called our habitat module that comes up with a score of essentially how degraded the land is. And what we do is we look at each patch of land, each parcel, and understand what kind of ecosystem it is roughly, and then apply kind of a basket of metrics approach to it. So for example, for a wetland ecosystem, we use something called NDVI regularity. If it's a forested ecosystem, we can really think about using something called Rouse diversity index. And then also for all these ecosystems, we also calculate ecosystem productivity, which is something, if I want to get technical for a moment, it's the rate of change of biomass production over time. So what that means is like, okay, how well is it growing year over year? Can kind of like abstract away like some of the biodiversity in the area to, okay, if everything is working well nicely on that plot of land, it should be producing, whatever it's producing in terms of a grassland or trees and relative to itself. We also then compare it to a baseline. So we find a baseline nearby of a similar ecosystem type or the same ecosystem type, run those metrics on there, and then we produce that nice score for that customer to understand. So basically, at the end of the day, the customer gets the results that say, okay, these are the best parcels nearby to restore that are suitable for a certain species. We ship that off to the customer. They give that to whoever they're working with or internally who's going to the ground to do that final analysis. They do that final analysis and say, okay, perfect. You've helped us out, weed out a lot of areas that otherwise would not be appropriate. On the kind of questions that the companies are answering for their clients. So when it comes to precision, what we're doing, for example, is we're doing a pre-diagnostic. And how this kind of plays out is that we're able to be a little bit less precise with our analyses. I mean, I think in general, when we're talking about remote sensing, you can't have like granular, super accurate precision on biodiversity data because you're not able to like observe a certain species in a certain time in a certain place. Maybe unless you had a drone very carefully, uh, hovering over something, you saw something, but this is not practical when it comes to actual business cases. And through this pre-diagnostic, basically what they do is they take the data, they say, okay, well, you've given us like all these sites that could be appropriate. Now I'm going to go to the ground and actually run the like we'll do the on-ground analysis, but what you've given me is like speeding up my entire process a whole lot. So that's how we use that's how we handle this kind of data precision problem. Other companies, perhaps those in the agricultural domain, might benefit more from higher resolution data, for example, with precision agriculture, regenerative practices being incorporated into that, and how that can be tracked and improved over time, doing MRV for this kind of thing. You could run a drone over it with a perhaps hyperspectral or multispectral sensor to understand certain crop parameters, like crop specific data that would allow you to kind of garner an idea of how well your approach is doing. Or even like with the notion of like how real time the data is another kind of dimension that is important. For us, we don't need super up to date data at like kind of, I guess, like saying it's real time. We can really get away with providing good information for our customers on a less up to date basis. Of course, it's always better if it's, up to date, but we don't need it per se. But for example, a company, doing something to track wildfires in real time or something like that would definitely need more up-to-date data. They might have a drone or might be using real-time satellite data or near real-time satellite data to map these kinds of features.
Something to have in mind is the size of the data. So just to think, what we're talking about here is often they're pictures. So they're pictures like the pictures from our phones. And if you go back, maybe not that much than 3 or 5 years ago, when you were taking a picture with your phone, it was 3 megabytes. Now it can go up to 10 megabytes. And you're kind of taking the same picture. But what's happening is the resolution of the picture you're taking is much higher. So what it means is that if you only like one part of the picture and you crop it, you still have a fairly good picture to print it if that's something you still do. So what's important to know is that there's some data sets that are 50 centimeters resolution. So you have information for every 50 centimeters. That's super high resolution. That's for some of the examples that Luc was mentioning. But that means that the amount of data you're working with is huge. So it depends if a company is working at a scale of the world, probably they can't be working with a 50 centimeter resolution because the amount of data they would have to ingest is massive. So once, if, for example, that company is interested in their supply chain and they're very interested in a part of the world where they are sourcing, after having worked with like medium resolution data, and that can be around 1 kilometer, that's is quite often a resolution to work with. If they really want to understand what's happening where they have some extraction of a certain material they work with, they may want to go further down and see with other tools with higher resolution. So again, it depends the question you're trying to answer. If it's first is to have an idea of what's happening in your whole portfolio, you may be fine with 1 kilometer, even sometimes 50 kilometers, but I would say 1 kilometer is good enough. If then you are very, like, you want to have precision of what's happening in a local area, you will have to go further down. But that means space to store the data, computer power to process the data, and all those things cost money. We are processing a lot of remote sensing and data model from remote sensing to then build up our own model. So it's lots of models. And that's why we need to go to the ground and check that our assumptions haven't been too naive, maybe is the right word, that our assumptions have been kept realistic. I think that's the way of putting it. So, for example, when we do species distribution model, we do them based on climate, because we understand that in this case, there's the element of the human action. So a species is where the species is because the species has managed to get there. But if you have the human that takes that species somewhere, your model can be a bit more like, oh, it's where the climate conditions are found. This is overly simplistic. There's modeling that can become more and more complicated, and that means more and more assumptions. So we like to start very simple, because that way it's easier to explain, first of all, but also easier to understand where the assumption has gone wrong, rather than start overly complicated and try to break it down. But yeah, so as inputs, we do have, as Luc mentioned, the land use. We have as well the climatic variables that are derived from I'm going to say it, climate models, and are validated with ground truth. The climate data is validated with ground truth data, and then we do something that is called in GIS, which is overlay, but it's overlaying lots of data, and at the same time having the data selected. So there's an element of curating, right? You don't want to have all the possible information in the world, because again, it may be very difficult to then understand what has been selected. Yeah, so it's a matter of creating a model that has clear assumptions that we can then validate afterwards with ground truthing.
So right now, what these companies, or how they're traditionally doing these operations, is working with these consultancies. And these are folks that are going to the ground. They have a lot of siloed knowledge with how the regulations work. They're going to the ground, sometimes driving around to different sites, looking at different sites by hand. Maybe they're using some GIS tools, but it's pretty manual work. They probably are not doing a lot of modeling. And if they are, that's cool. But I think what we're doing is really streamlining this process, really allowing for them to have something kind of objective as well, that can be applied again and again to different areas and different sites that our clients work with. And we're basically doing something that couldn't be done before by our ability to assess hundreds, if not thousands, of different parcels, just in a couple of hours as our algorithm clunks away at doing its operations. So I think that's pretty powerful.